So good evening here in Shenzhen, and good afternoon. I think Jelmer, you are in afternoon, and then good morning to anyone who is in the morning. I think Olga is in the morning. So wherever you are, whatever time you are, we are welcoming you to another tinyML talk. And today we have Jelmer Neeven, Neeven from Plumerai. As I don't know whether I pronounce that right, but okay. He's from Plumerai, and good, wonderful. And his topic today will be about data techniques that enable tiny computer vision in the real world. Yeah. So before we get to the talk, we would like to thank our sponsors, like for our strategic partners that are helping this community to grow and take us to the next level. And one of them is like Analog Devices, AON Devices, ARM, Deployed, Edge Impulse, EMSA, PhotoHub, Greenwave, Groovity Inc., IBM, Hotter, IMA, ImageMob, ITMIS, Clickertech, Lantel AI, Microsoft, Nota AI, NXP, OctoML, Prophecy, Quizo, Qualcomm, Reality AI, and you have Reason, yeah. And you have Resource, SAP, SIP Studio, SensiML, Silicon Labs, Sony Microconductor Solution Corporation, ST Light, and you have SS Stream Analysis, Synaptics, Synsense, Syntian, and TDK Inverses. Yeah. So just to remind you again, our next stop or our next upcoming talk, like on 38th, we have our tinyML on Devices Learning Forum that will be taking place online. It's a global activity that will be taking place online from August 31st to September 1st. So you're all welcome to scan or follow this link to join this program and sign up for the program. And sponsorship are also invited from everyone. Yeah. Then you also have the tinyML Neuromorphic Engineering Forum, and the chair will be like Professor Charlotte Frankel, something like that. It will be on the 27th of September, and you are also welcome to sign up for this. Likewise, sponsorship are available. You can reach out to us from sponsorship.tinyml.org. And then the next forum will be tinyML EME Innovation Forum. That will take place between October 10th to October 12th. And the keynote speakers will be Massimo Banzi and then Alberto Sangiovanni will be this. And the registrations are still open. You can still register before September 15. And you can follow this link to register for this event. Yeah, and likewise, sponsorships are still available. If you want to sponsor this program, you can just email us on sponsorship.tinyml.org. So like I have been saying, like tinyML has been a growing community. We have been growing exponentially, and we have had like over 10,000 members in 45 groups in 36 countries. So you are all welcome to join us by scanning these links or following the URL. And we also have an active community on LinkedIn. We have about 3,000 members on LinkedIn and 8,000 plus followers. So likewise, you can also follow us on LinkedIn for daily updates or weekly updates or projects that are done by the tinyML community members. So you can learn a lot from the community members by joining our communities. So you are welcome to sign up or join our communities. Yeah. Yeah, and also you should remember that, like, for example, if you sign up for this event or you want to watch this video or this recording again or previous recordings, you can find all our recordings on our link on our YouTube channel. And we have over 7,000 subscribers. We have over 441 videos with over 236,000 views. So feel free to go to the YouTube channel, and you have a lot of things to learn in this YouTube channel. Yeah. So yeah, who is Jelmer? Maybe you all interested to know who is Jelmer. Jelmer is a deep learning scientist and a software engineer, and he's passionate about building smart tools and real-world applications. He obtained his master's degree in AI from Maastricht University and has been with Plumerai for more than 3 years, and he spent most of his time building efficient or robust AI for microcontrollers. So through his research in novel architecture and like data techniques and training methods. So Jelmer, you can take control, and we can wait to hear what you have for us today.
Yeah, hi everyone. Thanks a lot for joining today. And yeah, like mentioned, I will be taking you through some of the tools and techniques that enable Plumerai to build accurate computer vision models for the tiniest edge devices. So first of all, a brief introduction to Plumerai. We are a startup focused on efficient deep learning in general, but we're mostly working on computer vision right now. Yeah, the application most relevant to this talk is our people detection product, which, given some camera footage, will detect each person in view, even if they're partially occluded. It will track people across time and assign them unique identifiers. It works both indoors and outdoors in various lighting conditions with standard RGB cameras and with active infrared footage. And its footprint is only 1 megabyte, so it really is tinyML. And in fact, our goal is to really make practical computer vision tiny. We want you to be able to deploy people detection anywhere, and that means it must be able to run on any device with minimal resources. And in fact, our people detection therefore even runs on tiny $1 Cortex-M microcontrollers, like the one in the picture there. And just to stress again, you don't even need any additional hardware for this. It is really just software update. It works out of the box on many devices: ARM Cortex-M, ARM Cortex-A, x86, RISC-V, and many more. So yeah, let's have a look at it in action. There are many use cases for people detection at the edge. For example, one of them is smart doorbells. So you can be notified when someone walks onto your property or into your garden. Yeah, you can get an SMS or whatever whenever someone leaves a package, or whenever someone enters your garden at night. It's very useful in offices, for example, to know when people are using specific rooms, how many people are in a given room at any given time, which of these desks are being occupied. And this can, for example, be used to turn on the heating or the air conditioning. So that's very useful. You can see here, it also works outside in low light conditions, which makes it very useful for security applications. Again, here it works with standard RGB footage, but it would also work with infrared. And there are many other use cases, from web conferencing to optimizing traffic lights for pedestrians. You can even run it on a battery-powered device if you really need to. And the image data really never leaves the device. So even if it would be feasible to run people detection in the cloud, the tinyML solution is not just cheaper and more efficient, but also a lot better privacy-wise. So how did we manage to build a tinyML product that is both this efficient and still robust? Well, there are various elements that come into play here, but they're all highly intertwined. So if you really want to do it well, that means you need to cover the entire stack. Which in our case means that we have our own hardware IP core. This is an AI accelerator that is the ideal companion to your RISC-V core. It fits on the smallest FPGAs from Lattice, Efinix, and Xilinx, or it can be implemented as an ASIC as well. We have our Plumerai inference engine, which is actually the world's fastest inference engine for ARM Cortex-M. It is 1.6 times faster and uses 2 times less RAM than TensorFlow Lite for microcontrollers. So this really makes a big difference to the practical application. Then, of course, we have our own custom tiny model architectures and training strategies. And then finally, we have the Plumerai data pipeline, which is what I will be talking about today. And unfortunately, the importance of good quality data is often overlooked in the deep learning community. People tend to focus more on things like architectures, but high quality data is absolutely crucial for developing an actual product, and even more so for tinyML, as I will demonstrate in this talk. So talking about data, how did we get started on our data journey? Well, the very first thing you will do when you're still in the product's prototype phase is, of course, have a look and see if there's any publicly available data out there that you can use. And in our case, there's this dataset called the visual wakewords dataset. It is a subset of the larger COCO object detection dataset. And the visual wakewords dataset is aimed specifically at microcontrollers. It has about 115,000 images, of which roughly half has people in them. And it comes with bounding boxes, which is very convenient. And the authors of this visual wakewords dataset even claim that this provides a realistic benchmark for tiny vision models. So in other words, it sounds perfect for our application, right? And yeah, so we took this data set, we designed our initial prototype model around it. And on paper, we did very well. We got a model that had high accuracy, small model size, and it ran very fast. So we were quite happy with this, and we were excited to take it out into the wild and give it a spin. And we quickly found out that the real life performance was just so bad that it was really unusable. It was really not suitable to use in any kind of product at all, even though on paper it looked very good. So what was the issue here? Here you see some examples of images taken from this visual wakewords dataset, where the images on the left are the negatives and the images on the right are the positives. And the very first issue here is that if you look at this image in the top left, the negatives, the context itself is already irrelevant. So for example, I can quickly tell you that there's not going to be a person in this image here, not because I've necessarily seen that there is no person, but just because I already know I'm not going to find a tiny person next to a toothbrush on top of a bathroom sink. So the context here kind of gives away the fact that there's not going to be a person. And one extreme example is actually the traffic light here. Because we found that because our models need to run really on edge devices, they need to be tiny, and therefore they have limited capacity. And it is this limited capacity that makes them prone to taking shortcuts. And in our case, one of our initial models had learned that because the sky is usually blue, and because the sky also rarely contains any people, whenever there's a large blue background, it would predict that there are no people there. And this shortcut was entirely valid on this data set that we trained it on, but it doesn't, of course, translate to real life. And then another problem, not with this data set, not with only this data set, but actually with public data in general, is that the images are often scraped from the internet. So here you see that these images they're obviously person-centered. Someone really took a picture of someone playing tennis here. It's not a picture of some area with a tenniser who kind of happens to be there. And this is actually a bias in public data because basically anything that people upload to the internet must kind of inherently be interesting enough to look at, because otherwise you wouldn't upload it. And that means that, this bias in this case means that the images are person-centered. So here the people are the obvious focus of the image, but if we would deploy a person detection product in the wild, then of course it's going to see many more images where the person is not obviously the focus of the image. So that kind of creates this gap between your data set and what your model encounters in real life. And so the lesson we learned quite quickly here is that even before we could start designing a good model, we very first needed to design a better data set. And we did. We built our own Plumerai data set. We are still using it to this day, and it keeps improving and growing. We've used it to train the models that I've just showed you. So we've been a lot more successful with this one than with the public one. And your question is then, of course, well, what is then the difference between our Plumerai data set and the public data set? And first of all, you can see that our images are not person-centered. So for example, here, this is just a room, and this is also just a room. In both cases, the focus is on the room. However, this image has a person here, and this image does not. But it's not clear from the context which of the two is going to have a person. So they're no longer person-centered, which is very good because, of course, the data our model is going to see in the real world is also not person-centered. And in fact, in general, most of these pictures are quite boring. For example, this is an image of an empty hallway, and so is this, and literally half of this image is a wall. And these are not quite interesting enough that you would upload them to Instagram, for example, and therefore they wouldn't be in public data sets. But they are, of course, exactly the kinds of environments that an actual product would operate in. So we really try to close this gap between the training data and the data that the model sees in the real world. And we have, of course, collected each of these images ourselves, but simply collecting images and then training your model on all of them is not enough to get a good model. If you really want to train a good model, then you need also good data tooling to make sure that your data is good enough to even allow you to train a good model in the first place. And this is what I will be talking about for most of this talk. So yeah, that brings me to the Plumerai infrastructure. Here you see the two components of our infrastructure that together receive about 90% of the attention of the deep learning community. And then here you see the overview of all the infrastructure that we have. So you see that you need a lot more than just these two components to actually build a real world product. And in fact, you see that half of these are colored light blue. I've done that to indicate that they are related to the data. So you see that half of our infrastructure is data related. So the data really is important and should not be underestimated. Of course, I would like to talk about all of the light blue ones, but I'll limit myself to the ones outlined in orange here. And I will start with the labeling. So let's say that you've set up some collection process and you've managed to collect a few million very high quality images that are very relevant to your target application. Then you want to train a model on them, but to train a model on them, you of course need labels. And the problem with high quality labels is unfortunately that they're usually very expensive and very time consuming to obtain. And this is true for image data, but it's even worse for video data. Luckily for tinyML, there is a very big opportunity that we can take advantage of, and this is auto labeling. Because in the case of person detection, or more generally object detection, we don't really need our boxes to be pixel perfect. Of course, we care that our model is efficient and that our model detects people when they are there and doesn't detect people when they're not there. And also the bounding box should hopefully correspond to the rough shape and position of where the person actually is. But we don't really care if the bounding box is 5 or 10 pixels off. And what that means is that we don't actually need our data to be hand labeled by humans, because there are many large off-the-shelf labeling models out there, increasingly large and increasingly good quality computer vision models, I would say. And they're not efficient enough to run on tinyML, but our labeling runs in a cloud, so that's not an issue. So we can use these off-the-shelf labeling models to do at least some of the labeling for us, and therefore save a lot of money and time on the labeling operation. However, it is important to keep in mind that even though these labels look quite impressive, they're not perfect. For example, here, this car is not even labeled. So even though it is quite convenient that we can use auto labeling, we do have to be very well aware of the fact that by doing this, we're actually introducing biases into our data sets that kind of translate from the labeling model into our own model, which we of course don't want. So you can only do auto labeling if you have proper tooling to identify and fix mistakes in your data set, and you can prevent them from translating to your own model. And at Plumerai, we have a bunch of such tools. Yeah, I'll show them later. But for now, yeah, basically once you have a labeled data set and you want to train a model, the first thing you really need is to set up your data unit tests. Because what most people in the industry do is they measure the performance of their model by computing, for example, the accuracy on some data set. But this is just a single number. It tells you how well your model is doing overall, but it doesn't tell you where your model is doing well and where it's not doing well. So what I mean by data unit tests are small but very specific collections of data. And one part of your unit tests should cover the things that you expect to encounter on a regular basis. So for example, we have a unit test that just contains pictures of empty desks. And we have another unit test that shows people that are walking through hallways at various distances. And the goal here is really to kind of to give you some indication of how well your model is going to be doing in real life in these scenarios. If we ship a model to a customer, we don't just want to say, yeah, we got 90% accuracy, so it's going to be good. we want to make sure that it gets the right accuracy on all the cases that are relevant to that specific customer. And then there's another part of your unit tests too, which should not cover the things you expect to see regularly, but the things you expect to see more rarely, and where your image or where your model tends to do badly. So for example, we have a plant unit test, and you may not immediately think about plants when you think about person detection, but one of our initial models tended to mistake large office plants like this one for people, not always, but some of the time. And you can imagine that this is quite annoying if you want to deploy your model in an office environment where people tend to put office plants. So of course, we fixed the problem, but we've also created a unit test so that now we can be sure that for each model we ship, the problem remains fixed and we don't suddenly reintroduce old issues. So then once you have your training data set and you have your data unit tests in place, you want to go through your training and validation data, and you want to make sure that it aligns with your goal. So in other words, you want to curate your data set. And there are many, many things that could potentially be wrong with a data set. And typically all of these are to some extent wrong with any given data set. And the first one is diversity. So if you look at these two images, there's nothing wrong with either of these images. I would say they're quite useful. But having 1,000 images from this single hallway is actually not very useful because it skews your data distribution towards this one hallway, even though this one hallway is, of course, not the only environment that your product will operate in. So if you have too many images of the same location or showing the same kind of thing, this can actually hurt model performance rather than improve it. Some images are simply not very relevant. For example, if I'm trying to train a person detection model, then neither of these images is very useful, simply because they're not taken from a perspective in which you would actually mount a typical person detection product. So again, there's this gap here between these two images and the kinds of images that the model would actually see in deployment. Then some images are way too difficult. For example, here there is, strictly speaking, a human, and they have been correctly labeled as such. But even if I look at this with my human eyes and brain, I cannot tell you if this is a human or whether it's a code track. So we cannot realistically expect our model to make that distinction either. So this image is just difficult to the point where it doesn't teach our model anything. But on the other hand, there are also many images that are too easy. So for example, this one on the right is, of course, very easy because basically all you see is the person. And this is useful in training your model initially to teach the concept of a person. But quite quickly, if you would have millions of these images, you'll start seeing diminishing returns. They won't actually teach your model anything, but they will, of course, increase computational costs and training time as well. And then there's simply mislabeling. So if you're not clear, even if you have human labelers, but you're not very explicit on what counts as a person or not, you might see some surprising results. So for example, this is, of course, not strictly a person, but conceptually it kind of is. And this ambiguity can lead to mislabeling, even if you have human labelers in the best case. But this is especially relevant if you use auto-labeling, because of course, for an auto-labeling model, it's even more difficult to make this distinction. And yeah, I've just given 4 examples here, but there are many other things that could be wrong with your data as well. I think this is a natural point to see if there's any question.
There are 2 questions. I'll just read the questions to you, and then, yeah. The first question is from, both of them are from the same person. They're all from Alexander Zubin. So his first question is like, how you figure out with your first model that the model treats the scene as without people once the background is blue?
Right.
I don't know whether you understand the question.
Yeah. Yeah, it's a tricky thing. So if you just take your model and you kind of walk around with your product in your hands and you see if it works or doesn't work, then this kind of stuff is very difficult to figure out. So we actually needed our data tooling to even realize that this was the issue in the first place. And later in the talk, I'll give a demonstration of some of our data tooling, and then I hope this will become more clear. But by having good data tooling where you can really kind of see all the mistakes you make side by side, then it becomes a lot easier to draw these conclusions about kind of shared reasons for these mistakes to occur.
Okay. So the second question is, do you have any distance limit? So all people say 10 meters away are not detected by the model intentionally, as they are far away and not in the area of not in the area of interest. So like, is there any distance limit for the model? Have you trained it for that or stuff like that?
So for the model, yeah, of course, it's always a trade-off, and it depends heavily on the use case. So for example, you can imagine that for video conferencing, where your camera is a webcam, then typically people won't be very far away. So then it makes sense to train a model explicitly to only detect people within a certain range limit, simply because it has limited capacity. But of course, in a security cam application, it's much more relevant that people who are far away are still detected. So based on the use case, we try to find a balance for this. So it's not typically one model that is extremely good at both, but there's usually some kind of trade-off. Yeah, but there's no inherent limit to. I mean, we see in practice that in the right application, we can detect people even beyond 10 meters. But yeah, it depends on the application.
Okay, good. And we have another one from the same person. Do you remember how many positive containing people and negative containing people images you have used to train the final version of your model?
How
like,
many?
Do you know?
In total,
how many?
we're speaking millions, and we try to have them. It depends, actually. It's a difficult question to answer because we have various stages of training that use different balances of positives and negatives. So it's hard to answer that question. But definitely we have millions of both positives and negatives. And sometimes they're balanced. Sometimes we try to focus only on the positives.
Okay. Yeah, so far I think these are all the questions we have.
Okay,
and
great.
Yeah.
Yep. Then
so I think I have one question. I just asked you that question and then you. Yeah. So we are talking about the data labeling aspect, the cost of data labeling, and the cost of data collection, because you were not trying to depend much on public data, right? You were collecting your own custom data.
Yes.
So how did you guys go ahead with this data collection without having to spend a lot of money, or maximizing the data without having to spend a lot of money? And then for the labeling as well, the tooling that you use for the auto labeling, like, is it a custom tool or is it a public available tool that you guys use?
That's a very, very thorough questions. So we, of course, we do try to use public data wherever possible. The trick with public data is often that there's like licensing issues and stuff. So it is quite tough to find. I mean, it is already tough to find public data that is even of good quality, and then it's even more difficult to find data that is that you're allowed to use, but that data does exist. So it is a little bit of a hybrid. That being said, so we've set up our own collection logistics, and we hired full-time people to actually go out kind of in the wild and collect images with various kinds of camera devices that we were interested in. And then, of course, once you've actually deployed a product, for example, you have some security cameras out there that are already being used, and it becomes a lot easier to collect images, but it doesn't become any easier to collect labels because, of course, the footage that it will send back is unlabeled. And that's why the data labeling, it's really nice that we can take this auto labeling shortcut. And there, to answer your last question, I would say it's a hybrid. We've both used public off-the-shelf detection models, but we typically try to kind of use them in a smarter way and add our own models on top and combine them to get even higher quality labels.
Okay, so just that you mentioned to the wild, that just remind me. I wanted to ask you one more question. I don't know how relevant will this question be, but my question is, like, at this moment, your model or your system is just detecting people, right? Do you guys have any objective of taking this thing to the wild, like, for example, for wildlife conservation? Because many people are doing this, especially like for us in seed. We are very concerned about this wildlife conservation, and we deploy so many things to the wild. So are you guys having any objective of taking this thing to the wild for wildlife conservation, sort of?
It's not currently on our radar, really, but it should be an easy extension of the technology that we already have. So it's definitely a possibility. Yeah.
Okay, no problem. So
Right now, it's
yeah,
not something.
you can go ahead. You can go ahead. Thank you
Okay,
for the answers. Yeah.
great. Yeah, so I've mentioned all these data
Oh,
issues.
I think we have. Just give me a second. Oh no, it's the same.
Okay, shall I
Yeah,
just
go
continue
ahead. Go
and
ahead.
then we do more questions at the end?
Yeah, sure.
Okay. So I've
Go ahead.
mentioned several examples of these data issues, but of course there can be many more. So yeah, the big question is now, of course, okay, knowing that typically all of these issues are probably in your data to some extent, how do you go about solving them? Well, the key here is to have this good data tooling that I talked about. So the most essential thing your data tooling needs to allow you to do is simply to identify failure cases. So you have your data and you have a trained model, and you need to be able to figure out why or where your model is failing. So for example, you look at your training data, your validation data, and you look at all the false positives, all the false negatives. Again, this is actually how we figured out the shortcut with the blue sky, simply by looking at all our mispredictions and seeing that, hey, there's some connecting theme here. And then as soon as you've identified a failure case, you want to actually create a specific test for that failure case. So for example, we might create a smaller subset of data with, let's say, a few hundred images of a blue sky. And the purpose of this test set is that we can actually quantify our model behavior on that test set, and therefore we can measure our progress. So then the next stage, of course, once you've identified a failure, is to somehow link the problem you're seeing to a problem that is in your training data. And this is a very interesting but very open-ended process. And I would say that this is what sets our own in-house tooling apart from the off-the-shelf offerings, because we've just not seen this kind of tooling. But yeah, some of the things that we do are, for example, looking at visual similarity between images, training classifiers to kind of say, okay, I have a few images of, let's say, a blue sky. Now show me more images that look like that or that meet that criterion. And another thing we do is looking at images that strongly influence the training process. And this all sounds a bit abstract, but I will give you a demo of our tooling right after this slide, so stay tuned for that. But for now, once you've found a problem in your training data, then of course you need to address it. And depending on which kind of problem you have identified, there is, of course, different ways of addressing it. But one thing you could do is correct the labels if you have mislabeling. You could do oversampling. You could apply some targeted training strategies. Or in the very simplest case, you could just add or even remove data. So there's many things you could do, but it's important to keep in mind that the quality is usually a lot more important than the sheer quantity of data. So definitely don't be afraid to remove data if it's not high quality enough. And then once you've addressed the problem, you're of course going to retrain your model on the updated data set. You can then reevaluate it on the test that you've created in the first step. And then depending on how well you're now doing, you can probably go through this cycle a few more times until the problem is solved. So this is definitely an iterative process. So yeah, let's have a look at some of the tools that we use at Plumerai. So one thing I mentioned is this training influence. Here you see our custom data tooling environment. This is just internal software, so don't mind its appearance too much. But we have various apps that we use. So for example, we have a way of viewing a data set, of comparing different data set versions, evaluating models, doing quality control on labels. And one of them is this training influence. So what I can do is I can select a specific model that we've trained before, and it will find some images in our training and validation data set on which this model has mispredictions. So in this case, it is showing us two images where the model has a false positive. So on the left, I think it's a whiteboard or something. It's classified as a person. And then on the right, there's like a chair or a leg of a table, which is also not a person. So what we're doing now is we're going through our training data and we're trying to find those images that specifically contributed to these two mistakes that we're seeing here. And here you see some examples of images that are in our training data sets. And you see some black boxes and green boxes. So the black boxes are just the people that have been labeled. And then the green boxes are also people, but those are the ones that are problematic. And in this case, I think it might be a little hard to see, but here you can see that there's a tiny little green box and the tiny little green box there as well. So there is actually a person in this image, but they're just way too far away to the point that they're just a few pixels. And what we're doing by teaching our model to predict those as people is basically saying, whenever you see a weird looking cluster of pixels, tell me it's a human. which is, of course, not what we want, because that's exactly why we're getting false positives on things like this. So what we're doing here is we just select all these images that show this problem, that have these tiny boxes, and then we can actually add a tag. So in this case, the tag I'm going to add is bounding box too small. And then when I show the tags, you can see that they're actually on this image now. But now that this information is saved in our database, we can actually use this information to modify the training process. So I would say that either we remove these images from training altogether because they're confusing the model, or at the very least, we need to modify the loss function so that the loss for these tiny boxes is different than the loss for the larger ones. So yeah, I've just shown you how we can go from a failure in our training or validation data set to identifying the images that contributed to them. But what if we find a problem in the real world? For example, imagine that we have a prototype model and we take it out for a test. And our conclusion is that, okay, this model actually works quite nicely. However, whenever we show it a desk chair, it tends to mispredict and tell us that this desk chair is a human. How do we go about fixing that? Then again, we have an app for this. So we open up our software again. This time we have a look at the similarity search. And what I do is I just go on Google Images and I find an image of a desk chair. It doesn't really matter what it looks like specifically, as long as it's a desk chair. And I feed it into this UI. And what this UI is going to do is it's going to search through our entire data set and find me the images that it thinks look similar to this image that I've just shown it. And you'll see in a bit that it doesn't return many desk chairs, actually. In the beginning, it returns mostly quite dark images, but there are a few desk chairs in there. So what I'm doing here is I select the images, even though they're very dark, that do indeed have desk chairs. And then I'm going to give this feedback to the tooling. So I'm saying, okay, these are actually desk chairs. The other ones are not. Update your definition of what is a desk chair, and then show me the new results. And you see that after one iteration already is returning way more desk chairs. So it's starting to understand what we're looking for here. But again, it's not perfect. This looks like a desk chair, but it's actually not. So we select all the other ones and not that one. And again, we give this feedback and we let the tool improve itself. And you'll see that after 2 iterations, takes a little while, but after 2 iterations, already it's quite good. So I'll enable the predictions of one of our models and I'll change the sorting of these images a bit. But you'll see that from this top 100, basically all of the images are desk chairs, which is very useful. And in fact, some of these indeed have a false positive. So you see here's a desk chair that has been incorrectly classified as a human. So what we can do now is we can select all the images of desk chairs and we can add a tag. And all the images that have been tagged now are our validation set. So this is the set that I mentioned before that we can now use to measure our improvement. And now that we have this set, we can specifically start looking for images that are not only a desk chair, but that our model is also predicting incorrectly on. So we have this thing that we call failure concept search, where it searches for a specific concept that also triggers a model failure. And after a few iterations, if we have a little bit of patience, you'll see that all these images that it now returns both contain a desk chair and a misprediction, which is useful because we can now use the influence process that I showed you before to figure out why we're failing on these images specifically, because these are in our training and validation sets. So again, I'm just tagging these with false positives so that we can use them in the future and we can use them in this other process. And then, yeah, now that this information is saved, we can really try to mitigate the problem. One interesting thing to note is actually that this is a false positive. Here you see a desk chair that has been classified as a person, but this is not actually a false positive. Here the model is correctly predicting that there's a person, but there's a missing label. This person has not been labeled as a person. So this one is easy to solve. Here, of course, we just need to properly label the images. And then this one, where a desk chair is incorrectly being detected as a person, we can use our influence tooling and figure out why specifically that is the case. So to recap, our tooling allows us to identify problematic images in various ways. For example, by searching for failure concepts, I can find first images that are desk chairs, and then I can find specifically images that are desk chairs where our model is not doing well. And then we can look at the influence of specific images on the training process. So given an image with a false prediction, for example, I can find the images in our training data set that contributed to this false prediction. And I can even find the specific boxes in those images that are problematic and that need to be addressed. But actually, the most important thing about our data tooling is that it's interactive and it allows us to act in real time. We're not just going through the data set and writing down on paper what we think might be going on. But as soon as we find any data of interest, we can find more data like that. We can immediately tag it and save this information in the database. And this information can then be used to modify the training process later on. And also, even more importantly, because this is fully custom tooling, we don't need to care about it looking pretty or being ultra efficient at all times. But instead, we have the flexibility to quickly add and explore new AI-assisted approaches like the two I've just shown. And these AI-assisted approaches are actually what makes this whole data iteration process scalable. Because in our case, we have roughly 30 million images in our database. So that's terabytes of data. And we just couldn't go through it by hand. So these AI-assisted approaches in this custom tooling are what allows us to build a data set at deep learning scale. Some other data techniques that I've shown in the demo, that I've not shown, but that we use are oversampling. So for example, showing a single image to your model multiple times. For example, if we have 5 images of a desk chair, then to make the most of them, we should probably show them to our model multiple times. Targeted augmentation, for example, if your model doesn't do well on dark images, you can explicitly make them darker or brighter. Prediction depth, which is a measure of how difficult an image is to your model to predict. And supervised contrastive learning, which is a way of kind of pulling apart representations of images that belong to separate categories. And this tends to improve robustness. So to conclude, our tiny computer vision models are not just efficient, but also very accurate still. And to develop production-worthy tinyML, you just need vertical integration. Developing good applications is a puzzle with many pieces, and you can only do it well if everything works together. And more specifically, this vertical integration is what allows us to rapidly iterate. As soon as we find any problem with the model, we can link it to a problem in the data. We can fix the issue in the data. And then once we have a high-quality data set, then we can finally train a high-quality model. And remember that all that it takes to run these models is a software update. Our vertical integration is also what makes it possible to do person detection on many existing devices out of the box without additional hardware. And then finally, if you're still not convinced after all this that the publicly available datasets are not good enough, all of these images are in a public dataset, and they're not actually as rare as you might think. So yeah, ask yourself if this is really what you want to train your model on. But yeah, that's it for me today. Feel free to ask any questions if you have them, and I'll be happy to answer them.
Yeah, we have, I think, 2 more questions or 3. Yeah, one of the questions is like, what algorithm do you use to get the similarity score of the images similar to each other, like using desk chair,
yeah,
for example?
This is actually a neural network that we use.
Okay.
So we look at we train our own network, and we see we look at the embedded features basically, and we compare those.
Okay. And another question is, how much of a person, like, do you have to see to say indeed it is a person, like the percentage of a human, like how much of the person does the model have to see to be able to classify that human as human?
Right.
Like, for example, let's say you just see my arm or my head or whatever. Yeah.
This is tricky because it depends on the body part, right? Like if I see 2 fingers like this, then already I can say with some confidence that there is a human somewhere here. But if I just see the back of my head, then that is actually just a dark blob. So it becomes way more difficult to distinguish that dark blob from a shadow or like a coat hanging on the wall. So it depends what part you're actually seeing. But yeah, definitely like a hand or something would be enough to recognize that there's a person. You don't need to see the full body.
Okay. Another question is, how do you measure the precision depth?
The prediction depth.
Precision depth, yeah. The precision.
That is actually, yeah, I think it would take a long time. I'll briefly try to explain it here, but this is just, you can find this online. But basically what you do is you divide your network into multiple parts, like multiple stages. And after each stage, basically the question you ask, like, okay, now that I've just done the first stage, for example, do I now have enough information to correctly predict the output of this image? Yes or no? And then depending on how many of those stages you need, that will be the difficulty score associated with that image. And this is interesting because that you can filter out.
Just take two 2 more questions, and then we will go ahead. And I have 1 more question, then we will go ahead.
Yep.
One of the guys said, "It's not oversampling bad for a model? Like oversampling, is it not bad for a model?" Someone asked this.
I mean, kind of, right? Like it is always better to have, let's say that you have 1 million images. Of course, it's always better if you have 1 million unique images than if you have like 1 image in there 100,000 times. But the reality is that it's often, it's definitely expensive and time consuming, but sometimes it's also outright impossible to collect enough data of a specific case. For example, you might need an image of a car upside down in the dark or whatever, and those might just be very hard to find. So then the best thing you can do is collect as many images as you can feasibly get, and then oversample those. But it is definitely tricky. Typically, you also need to apply extra augmentation, for example, to prevent your model from overfitting on the oversampled images. Yeah.
Okay, and the final question from the audience, this one is a little bit tricky. He said, "How does the influence analysis work? How do you figure out which training image contribute to the inference results?"
Yeah, that's a nice question. So basically what we do is we train our model and we keep track of the gradients during the training process. And then after training, basically the question we ask is, given a single model or a single image that has a misprediction, the question we ask for every image in our training data set is, if we would train the model on this image again, would that increase the loss on this incorrect image, or would it decrease the loss on this incorrect image? And then the images in the training data set that would increase the loss are, of course, contributing to this false positive, for example. And that way we can find the images that kind of need attention from our side.
Okay, that's fine. So 1 more question from me. Like you said, the model can be deployed on any hardware. And I just wanted to know, like, so far, how many hardware, like how many type of hardware have you tried it on? Because, like, for example, recently we have some camera sensors like this one, from like this one from SID, right? So actually you can run, they have embedded, they have pre-trained models on it that you can just deploy at once. And then when you have a specific problem, you can configure it towards your problem. So I wanted to understand, like, for example, if someone deploy your model on this kind of devices or on this kind of AI sensors, like, are they able to change the model or to customize the model towards their specific needs or stuff like that?
Right. Right now, no, because we've just kind of seen from experience that to really get a good performing model for some application, you need these data tools and you need a large set of high quality images. And therefore, we find it easier to just kind of collaborate with people. And they say, okay, I want your product and it looks cool, but I want it to do something slightly different. And then we will work together with them where kind of we collaborate in our data tooling to make that possible for them. But it's harder to kind of give them a product and then say, okay, you just try to make it work for your use case, because that is typically very difficult.
Okay, so this is actually a specific interest of me and also our team. But since we don't have much time, I will not bother the community with this, but I'll follow up with you with more questions about this thing, and then we will discuss further from there. So,
sure. You email me. My email is on screen. Or feel free. I think there will be a forum where people can ask questions. So if you have any more, then definitely let me know.
Yeah, like the audience can also go to the forum and they will see the link to your talk, and they can still ask questions there. And then you will also have access to it, and then you can always follow up with answers and stuff like that. And you can keep conversation on the forum as well. We always encourage this thing to have people to do their conversation on the forum as well. So it will help other people that we are not able to attend the event to learn in afterwards.
Okay.
So Jelmer, thank you so much for this wonderful talk, and it was very insightful. I think the audience can bear witness that it was a very insightful talk, and we hope to have you and your team once again. And then I will ask everyone or the audience to go check on Plumerai, and then when they need sensors also for their AI cameras, when they check on Plumerai, they can also come to SID and check on our AI sensors for vision. So we have as many as they want. So that being said, we'll just continue. Yeah. So thank you so much for attending today's talk. And before we close this activity, we would like to thank our tinyML strategic partners for committing to take tinyML to the next level together. And yeah, on that note, also we would like to thank the executive strategic partners. One of them is ARM AI. ARM AI is a virtual tech virtual tech talks, and yeah, you can check on them, and you can see the link on below to check on them. And you have Edge Impulse, the leading development platform for Edge AI or Edge ML, and it's a no code platform. If you don't know how to code but you want to do AI, you can just check Edge Impulse. And you have Qualcomm advancing AI research to make efficient AI unambiguous. And then you have Synthetine making Edge AI a reality. And our platinum strategic partners are deployed fast video analytics solutions on ARM CPUs. And then you have Kilkatech global IoT solutions. And you have Reality AI, the tinyML software that cover full engineering lifecycle. Then you have, Renaissance, and Renaissance is enabling the next generation of AI power solution that will revolutionize every industry sector. And you have Sony Semiconductor Solution Corporations. And our gold strategic partners are the analog devices, where what if becomes what is. And you have PhotoHub making over-the-air firmware and ML models update simple and accessible. And then you have Lantern AI. Lantern AI efficient inference platform combined with application template to make optimizing neural network for production inference in. Yeah. And then you have Microsoft. Then you have NXP. Together we accelerate the breakthrough that advance our world. Then you have Seed Studio deploying tinyML into the real world, plug and play groove models and sensors. So you have SensiML, the analytic tool suite. And you have ST Microelectronics provides extensive solutions to make tiny machine learning easy. And you have Synaptics engineering exceptional experience. And you have SynSense. SynSense builds sensing and inference hardware to ultra low power embedded mobile and edge devices. So our silver strategic partners are the following. You can check on our forum to visit them. And the next tinyML talk, don't forget to register for the next tinyML talk, and it will be on Friday, 19 August. And then they will be talking about optimization techniques, knowledge, and distillation. So on that note, I would like to thank Jelmer for sharing with us. And I would also like to thank the audience for taking your time to listen to Jelmer or to learn from Jelmer. And I hope to see you all on our next tinyML talk. Thank you so much.
Yeah, thanks everyone for joining.